Yeah, good. Okay, so last time I told you guys, well, today I'm going to talk about something we call it Boolean algebra. Okay, Boolean algebra, it is used in case of logic circuits, like what we are doing in this course. You will see some similarity with the normal algebra you learned before. Also, you will see some differences with the algebra you learned before. You understand what I'm saying? So here, as I told you, Boolean algebra, you know the algebra, I'm gonna call it normal algebra or the whatever you call it, the algebra you learned before. You know we have operations like addition, subtraction. I just want to make sure the mic is okay. Okay, so we have addition, we have subtraction, we have multiplication, okay, division. That's what you learned before. If you have f of x, x and y, it may, for example, equal x plus 2y, whatever it is, something like that. And every variable has a range of numbers. That's what you learned before, okay? The main difference between, or one of the difference, again, you will see some similarity for sure, but also you will see differences in this course because we are designing digital circuits or logic circuits. We're going to use the Boolean algebra. You can tell, you know the word Boolean. Boolean always means 0 or 1, right? True or false, okay? So one of them, still we have variable x and y and z or a, b, c. Still we have variable similar to this one, but the main difference is these variables are binary. You got what I'm saying? So here every variable can take only one of two values, either 0 or 1. This number one. Same thing for the function. So when you say a function of a, b, c, so there is this function is actually 0 or 1. You understand what I'm saying? This is a major difference between Boolean algebra and normal. There are other differences for sure we will talk about. I'm gonna give you more details. But for now, what we are gonna have here, it's like you have digital circuit. Okay. For example, you have here just an example. Just I want you to understand how we do it. For example, I have 3 variables. I'm going to use x and x, y, z for the variable. Sometimes you use a, b, c. It doesn't matter. It's just letters similar to the normal algebra. Okay. For example, here I'm going to use x, y, z, and then here at the output here we have f of x, y, and z. Okay. This is binary 0 or 1. This one's every one of these also binary 0 or 1. Okay. And inside here, we are going to use, again, we don't have addition, subtraction, division, multiplication. Okay. We don't have these operations. Okay. In case of Boolean algebra, we will use different operations. Like as I told you last time, the first operation we are going to use is a NOT or inverter. Okay. The second operation is AND, and actually from not here, for example, I can say f of x equal x prime. So prime here, this prime means it's inverter, okay, as I told you last time. Same thing, we have here AND. Usually for AND, I say xy, or sometimes I will say x dot y. So sometimes we put the dot, sometimes we don't put it. Again, this is not multiplication. We don't have multiplication here. This operator is AND. Okay. Same thing for x or y. So this is not plus. This is or. Okay. So these are the 3 main operations we're going to use here to create this function. For example, I can say just an example. If x, y, and z, for example, equals x, y or y prime z, for example. Is that okay? So this is a function. We have you can see you have 5 inputs, okay? And what's happening here inside here, this is a function. The logic circuit is gonna do this function here, x and y, or y prime and z. Okay? For sure, this function is not doing anything, but in the future, just this is for learning for now, but in the future, we will see how this function can do. We will do everything. That's what you should understand. We will do everything using these three main operations. Okay. What do you mean by everything? Like multiplier, addition, subtractor, decoder, encoder, multiplexer, demultiplexer, flip-flop, everything, registers, counter. So everything we will do using these three main logic operations. Okay. So one of the things also I explained. Any questions? Yes.
Is the order of operations for Boolean algebra the same as it is for standard algebra?
Yeah, I'm gonna talk in details about the Boolean algebra. You will see some similarity. You will see also some difference. Okay. So yeah. So here. So this is the first one. I have already explained this one before. The first operation we call it a NOT or inverter, and this is a symbol. This is the symbol we use for inverter. And I made it very clear last time. Every gate has electronic circuit behind it. Okay, and that's what you should see in the coming lab. Also, logic 0 should have a voltage. Actually, it has a range of voltages. For example, from 0 volt until 4.1 volt. Anything in this range, the circuit is gonna interpret it as logic 0. Okay, same thing for 1. 1, it has a range of voltages. For example, 4.3 until 5 volt. Okay, so anything in this range is logic 1. Okay, anyway. So as I told you last time, this is if you have any function, any logic function, in order to explain how this function behave, okay, what we do usually we can explain in one of two ways. Number one, I can do what we call truth table. Number two, we can do it using timing diagram. Here, I'm using it for only one gate. So I can do the same thing even if you have a very big function. It doesn't matter. You know what I'm saying? So once you have a function, either small or big one, if I want to know how this logic function behave, so either the truth table is going to tell me or timing diagram, just two different ways. Okay, they're exactly same thing, but this one like visualize. I visualize the action. Okay, so in the truth table, it's very simple. The way we do truth tables here, because that's what we do all the time. Actually, we have input and we have output. So here is the input, here is the output, and then you have to list here all possible cases for the input, and then what is the corresponding output for each input. Okay, here very easy. I told you there is a relation between the number of variables and how many possible cases you have. The relation is 2 to the power of n. Okay, so in this case, this is a very simple case because we have only one variable. That means so now we should have two cases. Okay, either 0 or 1. So here, this input x can have 0 or 1. This is only two cases. Is that okay? For sure, you know, in normal algebra, we didn't do that. We didn't do something like that because x can be like has infinite number of cases. You know, it's a different story, right? Because it is a range. Usually it is a range, but in this case, no. X can have only one value, either 0 or 1. And if x is 0, the output is 1. If x is 1, the output is 0. This is definition. This is how inverter works. Is that okay? Any questions? I can explain something here using what we call timing diagram. In timing diagram, x-axis here is the time. Y-axis, you can see it like a voltage or logic. So here, during this time here, x is logic 0. During this time, it is logic 1, logic 0, logic 0. And then let's look at the output, how the output looks like. It's going to be flipped, right? Because this is how inverter works. Okay? So here, this one is 0, this one is 1, 1, 0, 1, 0, 0 should be 1, 0 should be 1, inverted. So if this is the input, this is the output, how it should look like. Any questions? Okay, one more thing. You should learn in this lab, in this week lab, as I told you in the lecture, Actually, here, when here, look here, what I'm doing here, I'm gonna say this one is gonna change from 0 volt to 5 volt in 0 second. This is not the case. Nothing in the world, there is no any physical or quantities that can change from a certain value to a certain value in 0 second. Temperature, voltage, anything. You know what I'm saying? But anyway, so actually in reality, you can see some time to rise time and fall time. This time is very short, maybe in nanosecond, microsecond. Okay. However, just in this course, just because it's easy for you to here, I want to focus on the functionality, how it works. So I'm going to assume all signals are ideal signals. Okay, but in reality they are not, because it's easy for me to learn this way. But if it goes up and down, maybe it's difficult to capture or to understand, but you need. So I'm going to use ideal signals all the time, but you should understand it is not like that. Okay. One of the things also should learn in this lab and the coming lab as well. Also, it's here. The change happens immediately. That's what I'm saying here, right? So you can see here, once this one go to 1, this one is going to go to 0. Nothing in the world like that. Okay. Again, because this inverter has a transistor. The transistor, yes, the transistor is fast, but still it needs some time to open or to close. Okay, so it needs some time. So that's why in reality there is some delay. So it's not going to be immediately. There is some delay. Is that okay? Anyway, so the second gate also I explained last time is AND. Here in AND, this is the truth table of AND, just to make it easy. In case of AND, I think this is an easy way to explain it. If one input is 0, you don't need to think about it. If one input is 0, the output is 0. Okay. The only way to get 1 here is when all inputs are 1s. Here I'm making an analogy using switches. So in order for the current to flow this way, which is to get 1, so both the switches should be closed, should be 1 and 1. But anyway, so this is a truth table as you see here. So once this is the way, I think this is an easy way to compute AND. Look how I do it personally by myself. How I do it. Look here. I have 0 here, 0 here. Don't think about it. I don't care about what is there. So it's zeros. Okay. I have 0 here. I don't need to look at this one. It's 0. Okay. Now I have 1 here. So now I'm going to look at this one. Is that 1? Yes, it is 1. You got what I'm saying? So if you have AND here, and I know one input is 0, I don't need to know what are the other inputs. It's 0. However, if one input is 1, okay, if this one is 1, now I need to check the second one. If it is 1, so this is 1. If it is 0, so this one is 0. It's easy, right? Any questions? Again, it has electronic circuits that can do this functionality. But again, we don't care about, or it's out of the scope of this course, how electronics can do that. Okay? Same thing here. I can describe the functionality of the AND gate using timing diagram as you see here. So during this time, one input is 0, the other input is 0. That's why the output is 0. During this time here and here, one input here is 0, the other input is 1. So the output here is 0. Okay. Here we have 1 and 1. The output is 1. Okay. Here during this time here, this is 0 and 0. Sorry, 0 and 1. That's why the output is 0, 0 and 0. I'm going to get 0. Any questions? Okay. One more thing here, and this also may be important. Some gates, for example, the AND gate always we have one. The AND gate we always will have one input all the time. Okay. If it is 2 inputs, so in this case, okay, so it has to be 2 different gates. But this gate itself always has 1 input. Okay. For AND gate here, okay, I can make it 2 input, I can make it 3 inputs, 4 inputs, and so on. Okay, so I'm gonna tell you how. And even the chips you have in the future, as you will see, some chips have 2 inputs, some chips have more than two inputs. Okay, so actually, the way this one works is actually it is for example, if you have here W, X and Y, okay? So this is actually, you have here AND, and then this one should be another AND. Is that okay? So here you AND the first two input, and the result you can AND here. But instead of doing this way, I can just say we have only one AND here, and that's what I'm explaining here. You understand what I'm saying? So you have only, you can't do this in all gates. Okay, for example, as what I'm going to explain later in this course, we have something we call it exclusive OR. Okay, in exclusive OR, you cannot have three inputs, but if you have three inputs, it has to be done. It has to be done in two phases. It has to be done in two phases. Everyone has to be two inputs. Okay, so hopefully you are not confused. What I'm saying is, in case of AND, same thing for OR. Okay. You can have multiple inputs, but in reality, the way it is actually equivalent to this one. It's equivalent to doing it this way too, and then the output here I able to do another AND gate, but it's totally fine to do this way, okay? Because you don't need to do it in two steps, because it's easy for me to calculate the output of this function just using this one here, okay? How? I'm gonna tell you how here. Look here. Okay, so here this is AND gate between W, X, Y. Okay, this is the way we're gonna express Z equal W, X, Y. Again, I told you sometimes we put the dot, sometimes we don't put it. It's the same thing. Okay, so this means it's W and Y, and X and Y. Okay. Okay, so how can I do the truth table? Very simple. Again, how many inputs you have? I have three inputs, in this case, three variables. So how many different, this is the input the truth table should give you. This is input and this is output. Very simple. So how many cases you have here? Very simple. 2 to the power of 3. So I should have 8 cases. This is all possible cases. Okay? So 2 to the power of 3, which are 8. This number 1. Once I know they are 8, now you have to put all possible cases. Okay? And you don't need to memorize how to do it. There is a pattern you can do it. You got what I'm saying? What is the pattern? Look here, this variable half of the space zeros, half are ones. Okay? And this one, 2 zeros, 2 ones, 2 zeros, 2 ones. And then 0, 1, 0, 1, 0, 1. Once you do this way, I guarantee you have all possible cases. There is no repeat here. There is no duplication. So you can see the one row is not duplicated. So you have all possible cases here. Okay? Any questions? Okay. So this is all possible cases here. Now, let's calculate the output. How can you calculate the output here? Okay. Similar to what I explained before, guys. Very simple. If one input is 0, you don't need to think about it. If one input of the 3, even if this AND has 100 inputs, it's the same thing. If one input is 0, the output is 0. Very easy, right? The only way to get 1 when all inputs are 1s. Very easy. That's why the way I'm gonna calculate here, guys, I have here 4 zeros, so I don't even need to look at these ones. 4 zeros, so I'm gonna get here 4 zeros. Okay, very easy. Now this one is 1, so it's not gonna help me. So I'm gonna look at it. Here we have 2 zeros. So these are 2 zeros. Okay. Look at this one here. I have 1 0. So I have 0 here. The only way to get 1 when all inputs are 1s. Okay. So it's the same thing I explained for 2 input, same thing for 3 inputs, for 100 inputs, it's the same thing. Any questions? Okay. It's the same thing I'm going to do for OR as well. Okay. So this is OR gate. As I told you last time, for 2 input OR gate. The way OR gate works is, in order to get 1 here, it's enough to, if one input is 1, the output is 1. So it's opposite of what I did in A. So here, if I find one input is 1, I don't need to look at the other one. So just it's 1. Okay? Because it's OR, the relation is OR. Do this one or this one. 1 is enough. Okay? For sure, the only way to get a 0 here is when the 2 inputs are zeros. Again, sometimes we do it like switch analogy here. For the current to pass from point 1 to point 2, it's enough to have one switch closed. Closed here means 1. So if there is one input is 1, this switch is closed and then the current can flow. If you have 1 and 1, okay, that's more than what I need. Okay, but anyway, so again, look at the truth table here. Same thing, you have two inputs, X and Y. You have to put all possible cases. Again, there is a factor here. I know because they are 2, so I should have four possible cases. Okay, half of them zeros, half are ones, and then 0, 1, 0, 1. Okay. Anyway, how it works, as I told you, very simple. Once, look here, once I find 1 here, okay, I don't need to look at this one. It's gonna be once. Once I find 1 here, I don't need even to look at this one. It is 1. The only case to get 0 is when the all inputs are zeros. Is that okay? Same thing like AND, we can have OR with 3 inputs. We can have OR with 4 inputs and so on. Yeah, that's what I'm explaining. So this is, I'm gonna just repeat what I said about it. Same thing, actually. So this one here, this is the way we can, Z is equal to W or X or Y. That okay? So this one, actually, it is like you can take 2 by 2. So WX and then here Y. Okay, or you can just do one or this one, and that's what I'm explaining. So what is the truth table for this one? Again, I'm gonna just repeat what I said before. We have here in the truth table, we have input and we have output. For the input here, we have three variables. That means 2 to the power of 3 is 8. So I have 8 cases. These are all possible cases are here. Okay. And the way you have to do it for this one, half of them zeros and then ones. 4 zeros for ones, and then here 2 zeros for ones, 2 zeros for ones. 1 0 1 0 1 0 1 0 1, as you see. So these are all possibilities. Okay. Okay, how can you get the output here? Again, look for ones. Look for ones. So once I find here, all of these are ones, so I don't even need to look at this one. So I have 4 ones. Very easy. Very easy. Okay. Look at this one here. For this one, I have here 1 and 1. So I don't even need to look at the other inputs. So it's gonna be 1 and 1. Now look at these 2 here. Okay, so here I have one here, so here should be 1. The only way to get a 0 when all inputs are zeros. Any questions? Okay. I'm expecting now you understand. If I give you any function, what is truth table? Okay, you have to put all possible inputs here, and then you need to find what is the output of this function. Okay, because now it's very easy because you have only one gate. In the future, I'm going to do the same thing. Even if you have a function that has multiple gates, I'm going to do the same thing. Still, you have all inputs, but I need to do some calculation to get the output. Okay. So here, yeah. So nothing is new here. I'm telling you here, there is something we call Boolean function. Okay. So here, for example, you have here. This is like you can see it like a function this way. Okay. This function has 2 inputs, A and B, as you see here, and the output here, I call it F. Okay. A is binary 0 or 1, B is binary 0 or 1, F is binary 0 or 1. You got what I'm saying? And the relation between A and B is, so now, yeah, this is a function. Okay. So what I'm going to teach you now, guys, is number 1. If I give you a diagram like this one, okay, how can you calculate the function? Also, what you need to learn, how can you do the opposite? Sometimes I give you the function, how can you draw the diagram? Okay, very easy. Let's see. So what happens here? This one is B. This this is inverter, so this one should be B prime. This is AND. So what we have here is this input is A, this input is B prime, so it should be AB prime. Okay. Don't be confused. AB prime is actually binary 0 or 1. So after you calculate it, 0 or 1. Okay. Anyway, so here you have AB prime and you have C. So what's gonna happen? And this, this is OR. So this input or this one. So it's gonna be AB prime or C. Okay. So I can say this function. I have here AB, and then I have FAB is the output here, and FAB is actually AB prime or C. Is that okay? Same thing, similar to what I did before, guys. I can make, if I want to describe, again, this function is not doing anything, just this is for learning, okay? But in the future, I'm gonna make functions that can do useful things like addition and other things. You know what I'm saying? So same thing, if I want to describe how this function, the functionality of this function, if I want to describe how it works, I have to make the truth table, okay, for this one. So similar to what I did here, but this was maybe easy because you have only one gate, but this one here, we have multiple gates, okay? But still you can calculate it. So let's for example, do the truth table for this one, just to learn how can you do it. Again, how many inputs you have? I have two inputs. For example, here I have A and B. Because I have two inputs here, so we have four cases, right? So here I'm gonna say, for example, you have two zeros, two ones, and then 0, 1, 0, 1. These are all possible cases. Is that okay? And then for every input here, you need to calculate the output. What is F? Which is still can be 0 or 1. So I need to calculate what is 0 and 1 for this one. Is that okay? Let's do it here. For example, if this one is 0 and this one is 0. Okay. So here, I don't even to think about it. This is AND. And one input is 0. I don't need to calculate the other input. Okay, so the output here is 0. Okay. I'm sorry, I think I made a mistake. This one had 3 inputs, A, B, and C. I forgot C. Okay, I'm gonna do it again. I'm sorry. So here, I forgot C. So here we have A, B, and C. Again, so we have three inputs or 3 variables. So I should have 8 cases. Okay. So number one, we have here 8 zeros, 4 zeros, half of the space, 4 ones. So total we have 8. 2 zeros, 2 ones. 2 zeros, 2 ones. 0, 1, 0, 1, 0, 1, 0, 1. So these are all possible inputs. Okay. Now I need to calculate the output here F for this one. Okay. So again, you can take here, I'm gonna put here 0, 0, and this one is 0. And then you can calculate it and you see what is F. Okay. So for example here, as long as one input is 0, I don't even need to think about it. This one is 0 because this is N. 0 or 0 is 0. So the output here is 0. So when the input 0, 0, 0, this function is going to equal 0. Same thing for the other one. So here, let's do the other one. So here you have here 0. You have 0, but you have here 1. Okay. So again, because one input is 0 here, the output here is 0. One input is 1, so the output here is 1. So I'm going to get here 1. And then you can continue this way. Any question? Okay. So any function, that's what we do in this course. What we'll do in this course is, I'm going to use the 3 main operations I explained to create functions. This function can do very useful things as you will learn in this course. Okay. And for every function, you have input, you have output, and for the input, we put all possible cases. And then for every case, you need to calculate the output. Is that okay? I give you more examples here. So again, what you should learn for now is 2 things. If I give you the function, can you draw this one? Also the opposite. If I draw the circle, can you get the function? Okay. So for example, here, look at this one, this example here. Okay. So here you have C and D. So this one should be C or D. Okay, and then you have here AND. So this input is C or D. This one is A. So the output here is actually A or C. Sorry, A and C or D. So this one is binary. This one is binary, and then the result here is going to be 0 or 1. So whatever here is going to be 0 or 1. Okay, and then this one, whatever the value I have here is going to go to inverter. So the output has to be inverted. So whatever you put here, the result of this one can be 0 or 1. It's going to be inverted. Okay. Same thing, we have here B and E. So this one should be E, B and E, right? And then I do OR. By this way, I can. If you have this diagram, you can easily calculate F. So this is F. Any questions? Yeah, that's what I'm explaining here, guys. given, if you have a function, you can create a truth table to describe how this function works. You can also do it using timing diagram. It's the same thing, timing diagram or truth table, both of them have the same information. Both of them give you the same information, okay? So here, I'm gonna do it using truth table, okay? So as you see here, this is the function, it's actually A prime or B. A prime or B, okay? So how can I make the truth table of this one? Very easy. You have two inputs, as you see here, A and B. You have two inputs. So you have to put all possible cases for this one. The output here is actually A prime or B, okay? Just to make the calculation easy for me, it is much better to create another column for A prime. And then once I have this column, I can easily do here all between these two, and this will be the function. You understand what I'm saying? So just to make the calculation easy for me, as you see here, we have A prime and B. So B is given. So I already have B here. B is here. Okay. So all what I need to do is just try to have a column for A prime, and then I can do all between these two. Okay. So how can you do that? Very simple. So now the first thing I have to calculate, because this one is going to help me to calculate F. So the first thing I have to do is A prime. So what is A prime? A prime is flip of A. So here this one are zeros, should be ones should be zeros. Is that okay? Now I have a column here for A prime and I have a column for B. The function is OR. So I'm going to do here OR between these two columns, OR. Okay? As I told you in OR, I have here 1 and 1. Don't even think about it. 1 and 1. Okay? Here, 0 and 0. This is the only case that can give me 0. Okay? I have 1 here. Because you have 1 here, you don't even need to look at the other one. The output is 1. Okay? By this way, if you have a function like this one here, okay, this is the input of the function and this is the output of the function. I don't care about this one. I just made this column to help me to calculate the function. Okay, this is the input and this is the output. Any questions? Good. Yeah, maybe I don't need to spend more time on this one, but you see here, it's just, in this slide, I put a lot of examples. Okay, maybe 1 or 2 examples should be enough, but I put too many examples because I think the best way to teach this topic or to learn this topic is by learning or by studying many examples. So it's the same thing here. I give you here this diagram. I ask you to give me the function. Okay, so just very easy. Here you have y. So this wire, it's like a wire here, this y, and this wire is y prime. So you have here y and you have y prime here. This is x, and then you have x prime. You can see here, this input is taken from x. So this is x. This one is taken from y prime. I think there is a mistake here in there. Yeah. And this one here is actually, this one here is taken from x prime. This one is taken from y. So what should happen is, this one should be, I think this is a mistake, okay, because this one is taken from x. So it should be x, y prime. And this one is correct, x prime y, so y, okay? So this one is wrong because it has to be x and y prime, okay? And then the output here should be x, y. The output is correct, x. It seems to me I corrected this one, but I made a mistake this one. Anyway, so x, y prime, this one should be x, y prime, this one is correct, x prime y, so this one is correct, okay? Anyway, you have another, here I'm doing the opposite. I'm giving you the function, and then I ask you to draw the diagram. Okay? So the way you can do it very simple. Here you have OR. So now I have OR here. Okay. So here one input should be x, the other input should be y prime z. Y prime z. A. That means I have to show here and, okay, between z and y prime. In order to get y prime, I have to put inverter here to get it from y, as you see here. So here, one input is x, the other input is y prime z. Okay, so here one input is z, the other input is coming from y prime here. So I need inverter. Any questions? Okay. I'm gonna leave these two for you. Okay, it's just repeat, just to understand it. Any questions? Okay, guys. So now what I'm going to teach now is, look what I'm going to do here. I'm going to teach some theorems or laws or for the Boolean algebra. Okay, you will find some similarity to the normal algebra. You also will find some differences between the normal algebra and the Boolean algebra. Okay, you will see some differences. Okay. So here I'm going to give you some laws here. The first law, okay, by the end. So here I'm going to explain several properties and some laws here, and then at the very end I make a summary here. Okay. And what I did before in exams, in quizzes, I don't ask the student to memorize these laws. So I'm going to provide this slide during exams in anything. Okay. So you asked me about the order. So the order is given here. So we're going to talk about it later. So let's start with this laws here. So let's start with the first one here, guys. A or zero. A or zero. Okay. Remember, all variables here are binary 0, 1. So A or 0 should be A. Okay. This is the first thing. So any variable, A here can be X. Don't, okay, guys? So here I use symbol A or B, but it's the same thing if I use X or 1, just names, okay? So here, A or 0, it's actually should equal to A. Okay? Can you prove it? I'm gonna, okay, so one way to prove if these two are equal, okay? This is very important thing, guys. How can I prove if these two, both of them are equal or not? Okay, the way I prove it is actually using truth table. So here, what I did here is a truth table. I have here one column for variable A. For A, I have only two possible cases, 0 or 1, and then I'm gonna make another column here for A or 0, as you see here. Okay, and then so this is A or 0, and this is A. I can say these two are equal if the two columns are identical. Okay, so that's what we're going to teach in details later. But for example, here, guys, let me. Yeah. So for example, I wanna prove x or xy equal to x. I want to prove it. How can you prove it? Very simple. I'm going to use the truth table. I'm going to calculate x, which is this one, or I'm going to compare x. Then also I'm going to calculate this one, which is x or xy. And then I'm going to compare output by output. So if they are identical, that means these two are equal. Okay, guys? Same thing. So that's what here in this section I'm going to talk about equivalence. How I can say if you have a function f1 and I have a function f2, I have two different functions. They look different. Okay. So how can I prove these two functions are equal or not? How I can do that? One way to do it is you need to get the truth table of f1, you need to get the truth table of f2, and then you need to compare. They have to be identical. If only one row is not equal, these two functions are not the same. You got what I'm saying? So for example here, yeah. So for example, I want to prove this one is equal to this one. Okay. So again, I need to calculate the first part here, which is this one. I need to calculate the first part here for each different input for all possible cases, and then I'm going to compare. If they are identical, that means yes, this function is equal to this function. Otherwise, no, they are not equal. If there is only one difference between them. You understand what I'm saying? For example, here, I give you two functions here, f1, and I give you another function, f2. Okay? I'm asking you, is these two functions equal or not? Okay? Equal means for the same input, for all possible cases. For the same input, both of them are going to give you the same output. That's the meaning of equal. Okay? So I have to calculate f1 and have to calculate f2. Okay? So it's very obvious here, these are not equal because look here, yeah, this record is okay, this one is okay, this one okay, but I found one difference. If you find only one difference, you don't need to continue. You don't need to continue. If only one row is not the same, So my answer is the two functions are not the same. Okay, guys, you understand what I'm saying? So this is the technique I'm using here to. This is the technique I'm using here to prove this theorem and these laws here. So the first law we have is A or 0 is equal to A. Okay. A or 1 equal to 1. Okay. This one does not even need to prove it because I told you for or if one input is 1, you don't even need to look at the other one. The output is 1. However, I have proved it here. So here I have A, I calculated the second one, okay? And then I compared, here I compared. If you look at this one, E or 1, it's always 1. That's why it's equal to 1, always 1. Sometimes you have function that is giving you 0. So all the time it is 0. Or function that's always 1. So in this case, this one is always 1. So regardless what is A, so here I use the truth table to prove it, okay? Also, it is just by intuition you can prove it. I have another thing here, guys. A and 1. Or let's start with this one. Maybe this is the easy one. A and 0. I don't need to prove it, okay? Because if one input is 0, the output is 0. So this is the output is 0. So A and 0 is 0, actually, okay? As you see, I proved it. So when I calculated A and 0, I found this function is always 0. That's why I'm saying it is 0. Okay. A and 1 is actually equal to A. Can you tell me why? By intuition, I proved it using the truth table here. So here I calculated A and 1, and I found I got the same thing like A. They are equal. But yeah, by intuition, very simple. Look here, guys. If A is 0, I'm gonna get 0. If A is 1, I'm gonna get 1. You get what I'm saying? Because 1 and 1 is 1. 0 and 1 is 0. That's why, okay? Anyway, so this is all the laws we are gonna use. You need to know these laws. Okay, guys? Again, let me tell you what I'm doing right now. I'm explaining several theorem, properties, laws for Boolean algebra. And then we're going to use these laws later. I'm going to tell you how we're going to use it later. But for now, let's just see this one here. Next one. A or A prime should equal to 1. Okay. Again, I do it using truth table here. This is A, and this is A prime. And then I calculated A or A prime. I find it is 1 all the time. Okay. By intuition. I told you in case of OR, it's enough that one input is 1. So if this one is 0, so this one, I'm going to get 1 from here. That's why I'm going to get 1. Also, the other case, if this one is 1, okay, it's enough. I'm going to get 1. So you understand? But so by intuition, if A is 1, I'm going to get 1. If A is 0, the other one will give me 1. The other one will give me 1. Okay, that's why it always should be 1. Same thing, it's the same idea here. A and A prime is always 0. Okay, it's very simple because the only way to get 1 here when the two inputs are 1s, and it's impossible to have 1 and 1 here. You know what I'm saying? Because they are inverted. So these are 0, 1 or 1, 0. Any questions? So here, guys, we are going to use these laws here. We are going to use it in this course as a property or laws to do some algebra manipulation. Okay. Next one here, if you have A prime and then you have prime, so the complement to the complement you cancel, you return it to A again. Okay. So and I give you here how I prove it. This is A. This is the two possible cases for A. Okay. And then here we have A prime. And then I'm gonna tell, so A prime here, I just from here I can get A prime by inverting every flip the bits here, okay? And then I can A prime of prime, okay? So this one A prime. So I'm gonna flip it again, so I'm gonna go back to A again. So A prime. There is also something, guys, very, very important. Please listen to me because this is very important, okay? Look here, guys. Here, for example, I'm telling you A or 0 is equal to A. Okay. In reality, this might not be A. This, for example, can be something like A, B, or C, or 0. It's the same thing. So should equal to this one here. You understand what I'm saying? So here, yes, I give you only. Okay, but how I can know why you complicate? No, I'm not complicating it. You can simply say, I'm gonna assume everything here. I'm gonna call it Z. Okay, so I'm gonna call this one Z. So Z or 0 or okay. So this is like because this one here at the end should have 0 or 1, similar to A. So what I'm saying here, guys, everything I'm explaining here, yes, I explain it for only one variable, but it's still valid for if it is something else. Okay, as long as you have something here, whatever it is, and 1, you are gonna get whatever you have here. Okay, so you can have here, for example, A or B or C and Z, for example, just I'm giving anything. Okay, all of this and 1. Okay, so I'm gonna put this one, for example, I'm gonna put this one X. So you know X and 1 is actually X. Okay, so I'm gonna get this one again. Okay, guys, you understand this point? Okay. Same thing here. If you have A or B complemented and then you complement it again, so it should equal A or B. If you are confused, you can remove this one, call it X. Okay, so to be able to use this one. Anyway, next one here, A or A is A. A and A is A as well. Okay, let's see. For example, because these are identical, A and A, right? So either 0, 0 or 1, 1, right? So here, if A is 0, 0, 0, I'm gonna get 0, which is A. 1, 1 or 1, okay? Still, I'm gonna get 1, which is A as well. You understand what I'm saying? Same thing here, only we have 2 cases, either 0, 0 or 1, 1. Just only 2 cases. In this case, I'm gonna get 0, in this case, I'm gonna get 1. So this will be similar to A. Any questions? Okay. We have something, by the way, in normal algebra, A plus A is 2A. Okay, but it's not normal algebra, this is Boolean algebra, which is different. You can say this is A or A. Okay. Any questions? Good. Also, we have something here very interesting in the Boolean algebra. We call it duality. Duality. I'm going to tell you why it is very interesting. Okay. Look how it works. For example, if I have this formula, if I have this law or theorem, okay, you know commutative. We have also commutative in normal algebra. Okay. So normal algebra, 3 plus 7 is the same thing like 7 plus 3, right? So it's the same thing here also. But anyway, so here X or Y is the same like Y or X. So this is similar to the normal algebra. So look at the duality. The duality is very interesting, okay? Because you need for every law, for every theorem of every law, I can derive another one. We call it the dual. For any formula you have, I can derive another one, we call it dual. Okay? To calculate the dual, very simple. Any or, you have to make it and. Any and, you have to make it or. Any 0, flip it to 1. Any 1, flip it to 0. Again, for every formula you have, you can calculate another formula. And if this formula is true, this formula is true. How can I calculate? I don't need to prove both. If I prove this one is true, so this one is true. I don't need to prove both. You know what I'm saying? Why this is interesting? Because I can only know half of the formulas. Because the other half, I can calculate it using duality. So in duality, here, any or, I'm gonna flip it into and. Okay? Any and, also the same thing. If you start this one, if this is the formula, this one is the dual. So it's either way. So if you have this one, I can calculate this one. If you have this one, you can calculate this one. It works either way. Same thing here. You have and, I can flip it to or. And I can flip it to or. So this is how you have to do it. So any formula, if you have a formula and you are sure this formula is correct, I can calculate another formula which is also correct, and you don't need to prove it. Okay? The way you have to calculate the dual is any or, make it and. Any and, make it or. Any 0, make it 1. Okay, any 1, make it 0. You understand what I'm saying? By the way, this is the same thing I think I did here. So here, yeah, look here. So this one and this one are dual, right? Because here and it became sorry, or became and. 1 became 0. You got them saying, so these are dual. Same thing, these two are dual as well. So if you know one, you can get the other one. Okay? So here, or became and. 1 becomes 0. So let's look at the second next one here, which is also interesting. So we have here commutative. This commutative is similar to the normal algebra, right? It's similar to the normal. So the order, so here it doesn't matter. X, if you calculate x and y, it's the same thing like y and x. Okay. We have another one associative here. Also, we have here for associative here. Associative is, as you see here, if I have x or y or z, I can calculate these two first, and then I get the result then with this one. Or you can calculate this one first, and then you can or with this one. Okay, so it's the same thing here. It's similar. This is the same thing like normal algebra. If I want to add 3 plus 7 plus 5, so I can take these two first, calculate it, and then add to 5. Or I can take these two first, then add to 3. So this is not similar to the normal algebra. So if you want to do here associative here, if you have, I can take these two first, calculate them, and then the result do it with this one. Or you can take this one first, and then the result here do it with this one. Okay. So also this one has a dual. Again, in the dual here, any or, I'm gonna make it and, as you see here. Any questions? You need to know these laws because I'm gonna tell you we are gonna do algebra manipulation, okay, using these laws. So here I'm just to prove it, but later we're gonna just use them. Okay, so you need to know them. You don't need to memorize them, but you need to know how can you use them. Okay, because they are summarized here. I will give you this slide as I told you, but you need to know how can you use it. Okay. So here, yeah, that's what I'm saying. If you have ABC, so you can, this one is equivalent to this one, or this one equivalent to this one. Okay. Now, if I want to prove this associative law is working, for example, look, so here, if you have x, y, z, I can calculate x, y first, and then end with z, or I can calculate y, z first, end with x. Okay, so I want to prove these two are equal. How can you prove these two are equal? Using truth table, as I told you. Number one, here I'm going to put all possible cases because I have 3 variables, x and y. So I have to put all possible cases here, okay? And then here I'm going to get x, I'm going to calculate this one alone here in this column, here x and y, x and y. And then I'm going to calculate this one here, y and z in this column here, okay? So here, because this is and, we have 4 zeros here, 4 zeros here, okay? Here we have 0 and 0, so it should be 0 and 0. Just look for the zeros, okay? Here we have 1 and 1 and 1 and 1, so it has to be 1 and 1, because this is n. Same thing for y and z, y and z. Here we have 2 zeros, don't think about it, 2 zeros. Here we have 1 0, here don't think about it, 0. We have 1 and 1, we're gonna get 1. 2 zeros, don't look at the other side, the other input, I don't care. We have 0 here, should be 0, and then 1 and 1 if you want, okay? So anyway, so what I'm gonna do after that, guys, is now I have xy, which is this column here. I'm gonna do end between this column here, xy, and between z. Yeah, and then I will get this column here. So what I did, I calculated xy first, and then the result, I'm gonna calculate it with z, okay? Again, very, very trivial, very easy. Look how many, I'm very happy. Look how many zeros we have. 1, 2, 3, 4, 5, 6. Put 0, 6. 6 zeros. One input is 0, the output is 0, okay? And now, so I'm done until here. Yeah, and then I have 0 here, so it should be another 0. And then we have 1, okay? So now I'm gonna calculate this one. To calculate this one, I'm going to use this column, which YZ, so I'm going to calculate YZ first, then I'm going to end it with X. To do the end, first of all, I have 4 zeros here. I don't need to look at the other one, so I'm going to have 4 zeros here. Okay, good. 4 ones here. Okay, from the formula I have, if you have one input is 1, so the output will be similar to this one. So A and 1 is equal to A. Okay, so here, this one and 1. So here, I'm going to just copy. I'm going to copy this one here. Anyway, and again, if you look at these two columns, they are identical. As long as they are identical, that means these two formulas or these two functions are equal, it's the same. That's what we're going to do all the time in this course, guys. In order to prove that two functions are identical or equal, you have to get all possible cases for the two functions if they are identical. Okay? If there's only one row different, you don't need even to check the other rows. Only one row is different, they are not equal. Okay? Any questions? Let me do this one and then we can start the quiz. So we have a distribution here, and there is something interesting here because this will be different from the normal algebra because it's different. Usually students forget it. Okay, so let's explain it. You know the distribution, right? So in normal algebra, if you have 3x plus y, you know the distribution, right? So this one is equal to 3x plus 3y. Okay, you know this distribution. Okay, same thing. We have this one here. Same thing. If you have A and B or C, so I can do distribution. So this one will be similar to A and B or A and C. Very easy. So this one is similar to what we did in normal algebra. Is that okay? The interesting part, the part you will always forget because it's not in the normal algebra, it's not valid in the normal algebra, but it is valid in the Boolean algebra is if this one is odd, you can also do distribution. Look how I did it here. Look here. So A or B and A or C, and the relation is n, so it's going to be n. This is valid only in Boolean algebra, but it's not valid in, you always, even sometimes I myself forget it, okay? Yeah, because this is not in the normal algebra, okay? So again, if you have A or B and C, okay? So there is and here, right? So I can make distribution. So it's going to be A or B and A or C. Okay, guys? So you can make distribution whatever the operator you have here. And also this one is dual for this one. Dual. Why it's dual? Again, as I told you, any and make it or. Any or make it and. The dual. Okay? So same thing here. Any and make it or. Any or make it and. Okay? Any questions? Okay. Now I want to prove this one is working. Again, similar to what I explained, I have 4 possible cases for A, B, C, and then I'm going to calculate this column, B or C, just to help me to calculate this part here. Okay, so I'm going to calculate this one. Also, here I'm going to calculate AB and AC just to help me to calculate this part here. Then I'm going to compare these two columns together. They are identical. Because they are identical, this is a proof that this formula is correct. Any questions? Okay. This is for same thing, but for the dual. This is the dual one. Okay. Again, I'm going to calculate this one alone, as you see here. I'm going to calculate this one alone, as you see here. To calculate this one, to make the calculation easy for me, I'm gonna introduce BC. I'm gonna make another column here for BC, and then I'm gonna OR, as you see here, OR it with A. Okay. Same thing. In order to do this one and make it easy for me, so I'm gonna calculate this one, and then I'm gonna end them here. Okay. And then I can see here this is the proof because the two columns are identical, so these two are the same. Okay. Any question, guys? Okay, that's enough for today. I'm gonna continue next time. So now we can start the quiz.